Hello. So here we have a problem from harmonic analysis, and we are wanting to verify that for each integer n, this function here is L periodic. Now, a function is L periodic if for every theta, f of theta plus L equals f of theta. So the idea is that if we shift the input of the function by L units, or in fact a multiple of L, the output is just going to be the same as f theta. A common periodic function example would be sine of x, or sine of theta, which is 2 pi periodic. Now, we want to show that this function right here is L periodic. So we want to show that f of theta plus L is equal to f of theta. So it's a good idea to just write down our f of theta plus L and our f of theta, so we know exactly what we're looking for. So f of theta is just this value here, e to the power of 2 pi I n theta divided by L. Then f of theta plus L is going to be the same, except you're replacing the theta with this, theta plus L. So we have e to the power of 2 pi I n, and then we'll just put theta plus L inside brackets here, divided by L. Now we want to show that these two values are equal. So now we are left with these two values, and we want to show that these are equal. There's not really much we can do here with f theta to change it around. However, with f of theta plus L, we can distribute this 2 pi I n across the theta plus L. Anytime you're trying to show that two things are equal, it's often a good idea to work with the one where there's something you can do to modify it, such as factoring or distributing. So let's do that. Let's distribute this here. So if we distribute the exponent across the theta plus L, we're going to have e to the power of 2 pi I n times theta, and we'll just put this in brackets, plus 2 pi I n times L over L. Now, is there anything else we can do? One thing we can do is we can break this up into a sum of two different fractions. So if we take this left side and divide it by L, and then we add the right side divided by L. Let's write that down. So this is the equivalent of e to the power of 2 pi I n theta over L plus 2 pi I n L over L. And then there's just one other thing we can quickly do. We can note that we have L over L here, so we can cancel this out. So what we have here is e to the power of 2 pi I n theta over L plus 2 pi I n. Then, using basic exponent laws, this is the same thing as e to the power of 2 pi I n theta over L times e to this one here, this power here, e to the 2 pi I n. Now, look at this. If we go up, this is the same thing as f theta. So if we can show that this term on the right is equal to 1, then we're done. Okay, and we'll just explicitly say what we want to do now. So as established, this term on the left here, this product term on the left is equal to f theta. Now this term on the right of the product, we don't know what that is, but if it's equal to 1, then the product collectively is going to equal f theta. So let's just write down what we want to do. We want to show now that e to the power of 2 pi I n equals 1. And if we go back up to the question, we're verifying for any n in z. So I'll just quickly write that down here. Any n in z, which is a set of integers. Now, we're gonna make a small little note here. We can note that this value here, e to the power of 2 pi I n, is the same thing as e to the power of 2 pi I to the power of n. Now, if we can show this term here is equal to 1, then obviously raised to the nth power is also going to be equal to 1. And to show this, we're going to use a technique from complex analysis. This is just a general identity that's common in any 300 level complex analysis class. We can note that e to I theta, this is the equivalent of cos theta plus I sine theta. Now, we can apply this to this term here. And in this case, our theta is 2 pi. So we can then just note e to the power of 2 pi I to the n is the equivalent of cos, and then our theta is 2 pi. I'll just put that in brackets here, plus I sine 2 pi. And then this whole thing is raised to the nth power. Now, what is cos 2 pi? Cos 2 pi is 1. And then I sine 2 pi is 0 because sine 2 pi is 0. So we have 1 plus 0 to the power of n, which is going to equal 1. So we have shown that this value here, e to the 2 pi I n, is going to equal 1. And then what we can do there is we can deduce that this value here, because this value on the right is equal to 1, that this is just going to equal e to the power of 2 pi I n theta over L, which is just equal to f of 0. So if we backtrack, we started with f of theta plus L, and we've shown that regardless of what theta value we have, that this is going to equal f of theta. So we're done, and we've proved the L periodicity of this function.